Now we will be doing p-n junction diode. We have done p and n type semiconductors. You know, when p and n type semiconductors are brought close to each other, they are placed in contact very close to each other, then an arrangement is formed and that arrangement is known as p-n junction. So now let us see how is p-n junction diode is formed. So first we will take the example of the like n and p type crystals. Suppose you have taken p or n type crystals. In that case, what we do it here, just cut p or n type crystals into thin slices, and these slices are known as here wafers. So when the p type or n type semiconductors are cut into the thin slices and these slices are taken as wafers, and suppose you have taken one wafer like this, and in this one now, suppose if you are taking aluminum, you are diffusing aluminum in this p type, here is this one side, sorry, here this you have taken here the n type. So on n type semiconductor slice, if you diffuse aluminum, then the part becomes where aluminum is diffused, that becomes p type semiconductor. So by this way p-n junction diode is formed. Another way is here, if you have taken the p type here and diffuse phosphorus into this at high temperature, then you will be getting here the n type semiconductor. So by this way we form p and n type semiconductors. So now let us study here in detail how p and n junction is formed. Suppose I have taken a crystal here. In this crystal, this is actually here, this side we assume p type semiconductor and this side we assume n type semiconductor. These are the two crystals and this is the junction point here. Obviously, this p type semiconductor has got more number of holes over here and electrons are in minority carriers in p type. But if you take here n type, you will be getting electrons are here in majority carriers and in between these electrons there are holes which are in minority carriers. So now when this p and n type semiconductors are joined together, are brought in contact with each other, so see here this region where they are joining each other, diffusion of electron and holes take place because of concentration gradient. So when one electron diffuses from this side, it leaves behind here ionized state of the donor label here. So one positive ion is here and when the one hole is diffused from here, one negative ion is left behind. This is from acceptor. Similarly here, when the more and more diffusion takes place, you will see here at the junction, this n side you will be getting positive and positive, but here p side you will be getting negative and negative. So there are the ionized atoms to the n side, positively ionized atom and negatively charged ionized atoms are in the p side. Because of this, a current flows here due to diffusion of the electron and that diffusion current is to this side, that is called I diffusion. But this due to ionization at the junction, a potential gets developed and this potential or we can say electric field gets developed whose direction is from n to p. This electric field opposes further diffusion of majority carriers. It means this potential difference which has been developed at the junction is opposing the diffusion of the majority carriers. So this potential is known as here also barrier potential we call it, that is represented by V naught, and V naught we can take as a barrier potential. Now what happened due to this positive battery developed here? And because of this barrier potential, minority carriers come into motion. So the holes from this side will move to this side and electron from this side. So hole will move n to p and electrons will move here p to n. Because of that, drift current will be there and that direction of the drift current is to this side. So drift current is coming here due to electric field developed at the junction. And this region here at the junction where charges are immobile, this junction is known as actually here depletion region, depletion layer. or we can say here region. Larger the width of the depletion region, larger we can say the resistance of the diode, and smaller the width, we can say smaller is the resistance. So, this width of the depletion layer actually defines the resistance of the diode. So, now here in PN junction diode we have seen here formation of the depletion region and formation of the junction, here an imaginary battery that is called here whose potential is known as barrier potential, and also diffusion current and drift current. In equilibrium, diffusion current is equal to drift current. Now, we can show this thing by the graph also. So, when we draw the graph for the barrier potential here, we will be seeing the graph of barrier potential is like this. If you take this point, this is the 0 level here, this point is the highest here. So, this is known as actually here, this portion, this is the height of the barrier potential. And now, this is the variation of the potential across the junction, and this combination is known as PN junction diode, and its symbol is like this. So, this is the symbol for the PN junction diode. So, this we can say here PN junction diode here. So, this is the symbol for the PN junction diode, this is known as P type, this is known as your N type. So, now this is the formation of the PN junction diode.